Hi, Thomas. Can you hear me?
There you go. Can you hear me?
Yes, I can indeed. Very nice to meet you.
Very nice to meet you.
I'm Jonathan. I'm the chair of the meeting today. So it's
Good.
basically my role to bid you welcome and ask any questions you have, and then throughout the talk, lead the Q&A and that kind of stuff.
Mhm. Good. Good. Well, I'm looking forward to it. Did you get the materials I sent you? I guess you did. Yeah.
Let
Should
me
have
check.
gotten a kind of a summary paper, and then I did send through the PowerPoint just if you guys wanted to see it, but I can feed it from here.
Yes, I mean that is how we normally do it. Then
Yeah.
if you can
Yeah.
screen share, then that would be
Mhm.
perfect.
I'm an old hand at screen sharing.
I mean, we can check if it works before the
Sure.
meeting start.
Hmm.
Let's see. Yes, I got what you sent here. It was just the PowerPoint.
Hmm. Yeah, and then I sent the other day a paper last week, I think. I sent a paper. I know you guys got it. They said you received it. I
Ah,
don't know
okay,
if you
super.
circulated it. Yeah.
It's Reedy. She's the one who's primarily in charge of reading the emails and that kind of stuff.
Hmm. Hmm.
Yes, super. All right.
Jonathan, where are you from?
I am originally from Denmark,
Uh-huh.
but currently I'm studying in Switzerland.
Oh, good. Good. Yeah, I was going to say you're probably Danish. I have a very good friend named Hetchem von Spracular. We call him Sparky, and he's from Denmark. Yeah.
Ah, very cool.
Yeah.
Is he a colleague of yours?
He's the husband of one of my wives, my wife, one of my like I have many.
Yeah.
My wife's college friend, and he's a micro mechanical chip maker. He makes
Oh,
mechanical devices at the chip scale,
yes,
so pressure
yes.
sensors and those kind of things. And he's been doing that for. We're all old. I'm 70 and my wife is 60 and most of her friends are 60, 62, something like that.
Ah, I see. I see. Very cool. And where are you based?
I'm in Northern California, San Francisco Bay Area, a little town called Danville.
Right. So how is it time-wise for you? Is it, I guess it
The,
must be, yeah.
the town, I live in a small town what's called the East Bay. It used to be orchards years ago. It's now really just a bedroom community for Silicon Valley.
But I meant like time-wise, like is this very late or
Oh,
very early for you?
it's about 6:25, 6:30, something like that, which is
Okay.
no big deal. I'm up every day at 5 o'clock, so
Ah, okay, I see. Very nice. So this is
I'm
good timing for you.
I'm an early riser.
Hmm.
I didn't get to be 70 by sleeping late.
No, 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 no. No.
One other thing you may find interesting. In 2018, I died.
Oh, really?
Hmm.
Like in how?
I like in dead, like in had a heart attack, shocked me 7 times, did not recover. We're writing down my time of death, packing up everything to move on to the next victim, and my heart started back up.
Oh,
In
wow.
fact, that event is kind of why I came to learn about active inference because I started life as a microbiologist and I've been in business for years,
Hmm.
and
Hmm.
I got interested in the state that I was in, and at some point in time we could talk about that as well. But it was not like what you would expect, and it's really not. It's kind of like what you hear about near-death experience, but not
Right.
exactly. And it didn't bother me. It intrigued me to the point where I started to try to figure out how that state could be and how it relates to quantum mechanics and physics, and because I've got a pretty good science background. So I
Yes,
started
yes.
looking at that and thinking about it, and that led me into further and further. I was already working for 20 years on this concept of individually centric systems,
Yeah.
And it gelled it all down to understand that that everything from quantum on is either individually centric after it's decoherent,
Hmm.
or when it's coherent, it's one thing.
Hmm.
So if you think about quantum mechanics and you think about all the stuff we do in biology and physics and chemistry and all that other stuff,
Right.
for us to become in the physical world, we have to decohere, and decohering is the process of individuation.
And decoherence is that so
That's
my
when that's
mind.
when the quantum state. So in the quantum state, there's no time, there's no space, there's
Hmm.
just energy. What's
Hmm.
called a standing wave, right? And
Yes.
everything in the universe is derived from this standing wave of energy. And that's the core principle of this thing.
Hmm.
And I was working at the time managing HIV and AIDS patients, medications, therapy management, had a company doing that in the United States. And we were trying to figure out how to get a true patient-centered system so that the patient became the center point of the world, not the enterprise or the big business. And we worked on that for 15 or 20 years. And then after I died, I
Hmm.
came back to that thing and said, there's more to this than I thought there was. So I've been working on that now for the last, well, 8 years. And then I set a company up 3 years ago, 4 years ago now, to develop this technology. And
Yes.
I got to active inference because I was trying to understand the mechanics, the mathematics of this. And I'm not a theoretical mathematician by any means. But as I was going down this, I started reading Carl's work and other stuff, and I'm going, this is the mechanism, or at least a mechanism we can use to describe this process. So we've been doing that. And the reason for the presentation today is I've built the system.
Ah, very cool. Yeah, I read
So,
briefly the introduction and a bit
mhm.
about you, and I see a lot of the papers that you have written, or some of the papers are about consciousness, which I find very interesting myself. So that's also why I signed up for hosting this meeting. So I'm very much looking forward to
Yeah.
hearing your talk.
Yeah,
Um,
I write about consciousness because on the business side of the equation, the things that we're doing over there are going to be things that we're going to provide to the world, and some of that stuff is stuff I can't I can't talk about because it's going to be the core of what we bring out in this product. So
yeah, of course, of
consciousness is
course.
great because I can talk about it that way, explain it that way, have the entire conversation, and it has nothing to do with the mechanics of how you build that state. So,
Yes,
but I'm going to
yes.
show you today the mechanics of how we built this thing.
Ah,
So,
very interesting. I'm very much looking forward to it. So I'm just being mindful that it's gonna start pretty
yep.
soon, and
Yeah, it's about 6:28.
I am a bit don't understand why we cannot see anyone else yet. Hmm. Would you mind maybe in the meantime we can test if the screen sharing works from
Sure.
your end?
Yep. Hold on just a minute. Let me get here and you should see it should say IC Cognition Lab.
Yes, I see Corp Cognition Lab. Yes,
Uh-huh. Yep, that's working.
awesome.
Yep. Yeah, that's going to be the demo, and then let me put up my PowerPoint here. And
Yes,
you should see now ICFA Fractal Core.
I do indeed.
All right. So I'll take that down for now, and we won't share. We'll share that later.
Okay, sounds good. Sounds good. Mm.
And you're a neurobiologist,
I study neuroscience at ETH.
neuroscience.
Yes, yes. So I'm halfway through my master's degree, so I'm
Good.
still have a couple of semesters left.
Well, that's a great thing to do, and particularly in this day and age, because neuroscience, my prediction, Neuroscience is going to revamp and redesign the digital world.
Yeah, yeah. I'm really also looking forward to see what directions this is going to take, and especially now with all the AI stuff.
Yeah.
And
We use the term AI differently. We use the
yes, of
AI.
course.
AI for us is active inference.
Yep,
And
that has
my official position is there is no such thing as artificial intelligence because intelligence itself is a process. You can't have artificial process.
yes, yeah, yeah. So like if it has intelligence, then it's intelligence, not artificial, biological, or
Yeah,
however else we might categorize it.
we'll talk a little bit about that, what's called smuggling in things that you use to describe things.
Yeah, yeah, yeah.
Yeah.
Also, one more thing I need to make sure with you is that is it all right that this is gonna get published,
Yes.
the video?
Uh-huh.
Super, super.
Yep.
Good, 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 good. All right, I see we have some people joining already. Good to see you, Ian and Steven. And then I think it'll just be a couple of minutes, and then when Carl comes, then we can begin.
Good. 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 Good.
All righty. I think it's about time
All right.
that we slowly get to start. And so I'll start by saying hello, everybody. Welcome to the meeting today. We have Thomas Loker, who is here to present on some of the recent work that he's done. And yeah, when you're ready, Thomas, if you could give a brief presentation of who you are and what you're doing, and then we can slowly get started.
I'm an old man. I'm older than Carl. I'll start with that. And I met Carl about a year and a half, 2 years ago. I am a businessman and years ago was a scientist. I was a microbiologist. I have had a number of different businesses in my life, everything from funeral businesses and dry cleaning businesses to clothing and shoe businesses to computer businesses and franchise businesses and the whole range in between technology, non-technology, low-end, high-end businesses. I've been spent most of my life working with startup companies and have dealt with well into 250 to 300 startups other than Computerland. And when I worked at Computerland, we had 800 stores around the world. So I spent most of my life in business. My passion was science and have stayed active in science for quite a while. Not a neurobiologist and I'm not a theoretical mathematician. That will become painfully obvious, I think, as we start talking about this. A few years ago, I put together a company 4 years ago to start to work on a system called individual-centricity, which is what we're going to talk about, and a core underlying architecture that we call a fractal core. That's what I'm going to give you an overview of today. We have built this system. It works. I'm going to show you a demo of it working in a fairly simple way. It has a number of unique things about it. It is flies in the face of other systems that have been built. I've been in the PC business since the 70s, and I can tell you firsthand from the 1970s on in selling personal computers, most of the stuff we said about how computers worked was not true. Um, and the promises that we made in the 70s about how computers were going to change our life for the better, in some ways has been successful and delivered, and in some ways has not. And a great deal of why I think it has not has been the architectural structure that we used to build the system. So we're going to talk about what is fundamentally a different architectural structure. It doesn't require new technology. It doesn't require changing workflows. It doesn't require users to do anything different than use the system. We say it reweaves the fabric of the internet. So we're going to talk a little bit about it today. Um, I'll start with my presentation, so I'll share my screen. Can you see it?
Yes, yes, it's there.
Perfect. All right. So ICFA Fractal Core. ICFA is a product of Individual-Centricity Corporation. I am the founder, co-founder of that company with a gentleman named Yuval Lowy. Yuval is considered one of the top software architects in the world. Microsoft calls him a software legend. They've only named 7 in their entire history. He's one of the 7. He's been a friend of mine for 30 years. We're going to talk about individually-centric cognition, individually-centric systems itself, and we're going to talk about that via a hierarchical active inference structure that we've built that is now working. This graphic that you see here is kind of a description of what you're going to see in the demo. We've got a series of mazes, 3 different kinds of mazes that we're going to solve for. We have active inference, ICFA, individually-centric fractal architecture, and AI is not artificial intelligence, it's active inference. I don't believe artificial intelligence is possible, but I do think active inference works very well. And we're going to show you this system, and we'll have it compared to a number of machine learning or AI-based algorithms like random forest, Dynacube, Bayesian, MCTBS, tabula rasa, et cetera. And we're going to have active inference running side by side with those historically well-known systems. I'm going to start with a couple of little points. In the concept of the fractal core is described in a way to really take apart the world all the way down to a quantum level. Now, I'm not going to talk about quantum, and I'm not going to take it forward. We're not going to go through the derivation of the fractal core, but there are a couple of things that we try to stay focused on. Number one is we don't want to confuse the map for the terrain that we're working within. We mistake models for reality often. We do it throughout science. We talk about things, and we describe things often by what we say they are. As an example, we describe time by pointing to a clock. That's not necessarily a good way to describe time or where time comes from. We use foundational tests. If it can be removed without contradiction, can it be removed without contradiction? If it can, it's not foundational. Don't smuggle in what you intend to derive. I was talking with a little bit earlier about this. It's kind of like the idea of the clock. Don't use the description of the thing you're trying to describe in trying to define what you're trying to describe. We, again, do that quite a bit. So as we've been putting this together, these are some of the rules we've worked within. We think there's 4 hard survivors that happen when you strip away all the abstractions in a system down to the reality. You have a relational structure, you have normalization or unity in that form, you have topology and boundary condition inference, and these emerge, from these things emerge all the things we seem to understand as really abstractions in life. What is ICFA? The individually central fractal architecture. It's decentralized cognitive agents that are built using the free energy principle, extending renormalization generative models in a unique way. They have fractal self-similarity. They use active inference cycle at every scale. So instead of having to renormalize mathematically, we have an inference engine running at every scale in this system. You'll see it. It changes the way these systems report to each other, and it changes the need in terms of renormalization, I think. We have nested Markov blankets. If you're in active inference and FEP, this is not a new concept to you. Each node has its own boundary. They're conditionally independent between the levels. You'll see that again. We use precision-weighted communications, interlayer messaging that's weighted by estimated reliability. There is no central hub in this system. All the layers communicate with each other all the way up to the top layer. You'll see that in a second. We say this is not your mom's old enterprise-centric system. I'm bringing this up because the main difference between what we're doing and what everything else does, and I mean everything else, is we are individually centric in terms of how we look at the world. Our perception of where a transactional center is always on the individual thing at the edge of its Markov blanket, up and down the stack. Almost every piece of system and software that I've sold in the last 50 years has always been enterprise-centric. There's some major corporation, there's some major enterprise that is at the top of the stack that is trying to look all the way down and deal with all the things down below, and they become subservient to the top layer. In this case, there is not that way. It's flipped around. Every individual thing is its own center point. So all communication is happening between one thing and another thing, even if there's a series of layers of things going up and down. Again, you'll see that in real life. Again, this is kind of the same point at the beginning. We are rebuilding the concept of reality so that when we're focusing on answering a question in any given layer, the only thing we can answer the question from is what is within the layer or in the layers below it. We cannot go up to the abstracted layer above it and use that to define what's happening in the layer below. So we don't assume pre-existing actors. We don't assume certain things exist if they haven't come to exist yet. That's kind of just basically the same thing that becomes a fundamental for you to understand the individually centric world. Fractal core first principles. Boundaries create individuals. Nothing can exist without a boundary. It's not something, it's nothing, or it's everything. You've only got two choices in that answer. So for something to be an individual, for something to be a thing, it has to have parts that are the thing and parts that are not the thing. And if you don't have this boundary, you have no thing, nothing. So, or you have everything, if you want to get to the quantum side of the equation. Identity, confidence, and persistence. One of the things that we are doing with the product that we're building is called One True You. That's the first implementation of what we're going to build and put into the marketplace. It's going to be free, by the way. And what One True You is a thing that verifies people's identity. It verifies their identity by being able to look at them with sensors from their cell phone, determine the patterns that they exhibit of behavior based on the environment they happen to be in and how they have behaved before. So we look and predict what the next thing looks like it's going to be. If I'm going to pick up a coffee cup and I start to pick it up, what are the basic movements I should be doing in a minor form that I can measure and look at? And when I behave the way I'm supposed to be, clearly I am the person I am expected to be. That's what we do in One True You. And it comes from the concept that identity has to be confidence and persistence, meaning for this thing over here to have evolved, it has to be consistent. It has to be constant, and it has to continue to participate in its existence. If it doesn't, it's not a thing anymore. It can't, if the Markov blanket falls apart, it's no longer a thing. Time is bookkeeping, not flow. This is a big deal for us. We don't look back at what's going to happen over time. We look at precedent outcomes. So if I want to pick up a coffee cup, I have to be able to move my hand from here to pick it up. It has to have certain things that exist for me to pick it up. It must have some way for me to grab it, one. I also have to have control over my hand, two. Those are all precedent outcomes. I don't need to worry about time. I need to worry that that precedent outcome has been achieved so I can achieve the next thing. And that lives in the world when we start looking down a stack of information, looking for why something didn't, why it erred out. Is we're looking for a precedent outcome that failed, that erred. So there's that piece of that equation. And because it's fractal, the same thing exists at every scale. In every scale of the system we built as a fractal core, it's identical. It's not trained. It doesn't have anything happening at the beginning. It learns from square one, and it operates and coordinates with all the other fractal cores in the system, up and down the stack, whether it's at the smallest Markov blanket, in a Markov blanket with other things, and with other things and other things. At every stage of the hierarchical level, there are Markov blankets that exist within the thing itself, except down to the primitive layer, and that we have a fractal core that can operate in any one of those things. We don't put them in everything because we don't really need them in everything, but we could. And at some point in time, if we figure out one little piece, we may do that. Unlike Carl's current version of active inference, we use an ELBO, an evidence lower bound, for the baseline of what we're doing, but we also create what we call a cube, a confidence upper bound extension. And what that does is that sets a cap on the upper limit. When we get to a certain point in this variational measure and we reach this plateau area, then we use things between one layer and the next layer up to determine what kind of other thing we might do, what kind of other process we might take. So the confidence upper bound is a point at which we might choose to use a different algorithm as an example, or choose to run a panel of experts. It's more of a mechanical system that we're using at this point to help make a decision and see if there's a different way for us to run very quickly. By and large, it's a stopgap. It's a protection level. We are using phi right at the moment, the golden ratio, not because of its the theory of metaphysical things about the system, but we're using it right at the moment because we had some independent verification from Juval and I's paper on causality of time from 3 researchers working in health, one on epilepsy and seizures, another on myocardial infarction and the creation of heart, or not the creation, but the evolution of a heart attack, and actually another person working on Alzheimer's disease, who all came back and started talking about at these given points, which we identified in that paper, these given points, they're seeing things physiologically happen. I don't know why they're happening. We just started to use this as to test it ourselves. We're still using it, not again because of any metaphysics, just because it works. It may not be the best number. I don't know yet. So I just wanted to make that point. Renormalization. One of the first conversations Carl and I had was I sent him a paper, or sent him an email about pixels to planning and renormalization and the need for renormalization in fractal architectures. I asked him I said, if you have a true fractal architecture, do you need renormalization? I wouldn't think you need it. He said, yes, you wouldn't need it. That sent me on a quest, and I've had a couple of things, and that's kind of how we got to this one little discussion we're going to have today about renormalization. If we do this right now, it doesn't seem we need to renormalize, and it seems to save a lot of processing time. So that's one of the reasons for the presentation. So this is how the world exists in the state of where Carl uses it. And if I'm wrong, Carl, I know you will correct me, and I could be. And on the other side, this is what we're looking at and how we do it. And we look at inner blanket outcomes, which are already at the native scale. So within any given blanket, it's at scale. The fractal core is running at scale. Active inference is running at scale. And what's happening between the layers is just communication. So it's a reporting up and down, and the scale problem seems to not exist. So that's the idea that we're working on. Our cognitive lab, you're going to see we have 3 grids. That one is basically an open grid, one is a sparse set of obstacles, and another is a maze. The systems have to learn to navigate from one point to another all by themselves. We are not pre-training any of the ML models. They have to train themselves as they go. That's the fundamental test. Whether it's fair or not, you can argue. From my perspective, if active inference can do it without training, then they should be able to. And I say that tongue in cheek. And then these are kind of some of the results. That won't make much sense till you see it. Some of the open questions that I have, that is one of the reasons I'm starting to talk around, is ICFA actually doing implicit renormalization? In other words, are what we're performing another form of renormalization, which is possible? Or is it something where renormalization truly is not needed? So I'm trying to find out from a definitional point of view whether what I'm saying is correct or not. Two, hidden state interference. Our lab is fully observable and extends, the system we're using extends to behavioral biometrics, and it requires inferring latent causes from raw sensor data. So I need to understand this more because this is an area where I'm not 100% sure I understand how to take this forward. We have tested our system with behavioral data or with data we're monitoring that can be extrapolated into behaviors from cell phones. And we're finding that we can do good predictions with it from a standard cell phone as people use the phone in their day. And we can correlate that temporally and spatially into activities they do during the day. And then partial prefix credit. When a composite succeeds, which you'll see in a minute, steps 1 through 4, but fails at step 5, should the hierarchy assign a partial credit? Right now, we are not doing that. Right now, we have a variational measure. But if it succeeds in those, we're just kind of setting them to the side. We're doing nothing with them. That's one of the other questions we have. Oh, sorry. And then the last is, at this point in time, we're not using a D matrix. And the reason is we want the system to be able to, in effect, plug into a sensor and immediately extrapolate the primitives. And we've been able to do that right at this point in time. We have a lot more testing to do. But so far, we've been able to get active inference to be able to identify its own primitives. And then ultimately, this, I don't know why I put this in there. There's a book that I'm working on that's about the fractal core, and it's related to the overall understanding of consciousness. And it starts all the way down at a base level of understanding, and then it drives itself up all the way through to consciousness and ego, step by step by step. I'm not done with that. I'm still working on it, but that's really this point. Any questions before I go to the demo? All right. Let me get rid of this. So here we are. So I'm going to orient a little bit what we have. So this is an open grid. There's going to be a series of things we're going to look at. There's an obstacle course, which the agents have to go through, and there's a recursive maze. In the grid, we have right now a series of machine learning algorithms, and then we have what we call the ICFA baby, the Individual-Centric Fractal Architecture baby 7. This is version 7. Why do we call it a baby? Because a baby starts life with no preconceived knowledge. It has to learn how to focus its eyes. It has to learn how to see. After that, it has to learn how to distinguish sounds. It has to learn to figure out how to move his fingers up and down. I spent one Thanksgiving day with my nephew, who was about 7 months old, watching him learn to crawl up and down stairs. Most fascinating day I think I've spent, as I watched him literally learn how to get his foot or his hand up on his hands and knees, crawl up steps, and do it without falling down. And he did fall once or twice and had a negative outcome, as they say. So we've built this whole system around this. These systems, if you don't know what they are, ask. They're just 3 or 4 others. We have more than them. We have about 9 or 10. We have random forest and Q-learning. These are older systems. The current big dog in this group is MCTS, which is Monte Carlo tree system. That's being used by a lot of people like Claude and some other stuff. So we're going to compare against them. Um, there's a page that we'll go in and we'll look at. It will have a series of resources. We're going to talk about energy consumption in processing. We're going to talk about memory utilization. These things are going to run on the edge of a network on a cell phone or an IoT device, so they can't use a lot of power. We have a series of different measures and things we're going to look at. We won't go into this in detail today, but we can go into it another time. We're going to look at how the brain is being formed. I think you'll find this a little bit fascinating. So you'll see in here a legitimate look at how this thing is going to run. By the way, you're going to see the motor primitives are north, south, west, east, northwest, northeast, southwest, southeast. If I had just fired this up and not run it once to make sure it was working, these wouldn't exist. They come within 15 milliseconds when this thing starts. It figures out that those are the possible moves given the circumstances. Then there's an instruction for this lab and then what it's all about. In about a week or 2 weeks, you'll be able to download this and use it yourself. And there'll be a guide that will help you create, if you know how to do Python programming or Java, or use Claude or one of the other coding systems. You'll be able to create your own models and compare your models to this one and how we've got this one constructed. So that's kind of the idea. So what I'm going to do right now is I'm going to go ahead and start running a couple of tests. I'm going to start because I want you to see, we're going to start on the open grid. And I'm going to start with the grid running, and then I'm going to go back over to the architecture tab, and I'm going to show you as the brain starts to form. This is very simple. Again, we have the start point up here. We'll say the mouse is going to start here, or mice will start here, and we'll use this little red block, and we'll call it the cheese. There is a sense of smell in this environment. The cheese has a smell. The smell is mathematically calculated to dissipate just the same way sound would dissipate over distance, or most smells dissipate over distance. So it is not a ubiquitous smell. It does not have the same thing all over the place. It's not like a little radar beacon. And in an open environment, it has one characteristic. In a closed environment like the maze, it has a different one. So I'm going to go ahead and start it. And you'll see ICFA has already figured out a diagonal line is the most optimal path, and they're going MCTS, which is just fairly good system, is right behind it. We're going to go over the architecture tab, and you're going to see that the brain has already found that there are three key moves: southeast, 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 southeast. It has calculated these moves from the basic primitives. And it's realized right now, this is the most optimal, the most efficient. These exist, but this ends up using less energy than these use. So now it's running. What you see up here is this is one fractal core here. And you see here, there's a fractal core here. There's also a fractal core inside this layer. Now, right at this point in time, it's not being activated. We haven't turned it on yet at this level. We'll turn it on in a week. We're trying to figure out how to code it, and we finally have it down. And they didn't get it done for me to show today reliably, so that's why you're not seeing all three of them. So right at this point in time, there are three fractal cores, three active inference systems running simultaneously in this. And this thing's running along fine. We only have one layer. Nothing's going on. It's all good. And if I go back up here, you'll see that ICFA, the active inference system, is running just fine. It's going straight down. It's already done 22 paths, and it's running reliably. It's now at 23. Some of the others have had some wins. MCTS is at 14. Tabula rasa has made one successful pass. Bayesian has made 3, which I don't think would surprise Carl whatsoever. If you look down here, the learning rates, what's going on, they're starting to learn. They've had some successes. They're getting better and better. you will see that ICFA is at 40 steps. That's optimal. It's found the optimal path. It's going just fine. Now, this is all about learning. So we're over here. It's learned one thing that it needs to do to get to the cheese, and it's getting cheese reliably. What happens when the world changes? What happens if something goes wrong? So these guys are operating, they're kind of working their way around, but let's go in and let's throw in a monkey wrench. Let me put in a little barrier. Well, we've already figured our way around it. We can see the obstacle, we smell it, we're going down, boom, we're right back there. ICFA is back, it's already figured it out. Some of these will get stuck, some of these will get caught in the corners, but more importantly, what are we learning? Wow, we've learned a whole lot. The system has already learned a number of moves to solve that problem. Before it was it was southeast, southeast, southeast. Now we've got a southeast, northeast, east. We've got other moves that is picked up along the way. As this continues to run, it will add some other ideas of things to do. It's created a new layer. You see it's got a layer with a fractal core running. It also has these gold boxes are instances of a Markov blanket where we've applied a fractal core. So because the fractal core is bringing additional efficiencies, these aren't being used enough to apply one. So we're saving energy. This fractal core can communicate with these, can't control it, but it can control this and communicate up and down. What's happening here? The blue lines that you see are the constraints that mama, the goal, the outcome we're seeking, get me the cheese. We call this mama for a reason. If mama's not happy, nobody's happy. So mama is telling them what she wants to get done, all the fractal cores in the line. She's telling them what she wants to see, the constraints, and then they're telling her whether they've got an error or not. So the red bars you see is an error, that something missed. So we could go into this a little bit more later, but when you see a dash over here, this is saying that it fired 157 and it did not fire the second version of it. It was a problem. So mama then tells it a constraint and it goes all the way down and gets the primitive. So when the primitives are being hit, it's because in this stack of options, it didn't find an effective answer. So it's only hitting these when it's necessary. You see now we've got 5 layers operating in the brain. Each one of these is a deeper condensation of things that happened before, a composite set. So a composite fractal core gets put in the ones that are used most of the time. Sometimes there's 2, sometimes there's more. So this is all learning and going on dynamically. If we let this run for 2,000 or 3,000, 4,000, 5,000 steps, this will actually start pruning those things that are no longer necessary. It will never prune the primitives, and I'm going to run into a graphics issue in a minute. I got a lot of things going on. It never proves the primitives, and it never prunes the L1 levels. They're always there as a fallback. But these other levels will get a little bigger, a little smaller over time. And if I go up one level, if I go here, you can take a look at the overall efficiencies of the level. Now, at this point in time, layer 5 is being used about 7% of the time. And you see going over here, still most of the stuff is being done at layer 1. If we let this run for 15 minutes, 20 minutes, you will see what's going to happen is these things will start to condense a little bit here, and ultimately the one up here will start doing more work. This will grow, these will go down. But most importantly, start looking at how much energy active inference is using against the average of the other ones. And Bayesian uses almost nothing, by the way. It's a very low power system. So when you look at they're about 1.2 microjoules per step, and this is about 0.7 microjoules per step. And this will continue to go down. We look at the memory utilization. We're less than 0.3 of a kilobyte. They're at about 45 KB in terms of the CPU memory. So you go, these are just looking at the layers. This is awesome information that will be fun later. Simulated compute. This is the amount of compute energy per cycle. MCTS is very heavy. It's one of the dominant ones today. It's 3.1 microjoules, and we are down at about 0.6 microjoules. And we will keep getting smaller as we learn more. This is how the layers are playing. These are the layers. This is starting to get more and more utilization. It's becoming more and more the dominant layer in the past couple of minutes. And that's all on the simplest system that we have. So that's this. Now, let's go over to what is cognitively a little bit more difficult. In fact, in many ways, this is cognitively more difficult than the maze will be in a minute. So I'm going to go ahead and do the same thing, same group, nothing different. I'm just going to have it start to run. It's going through the obstacle course and it's finding its way down. I'll go back over here and you can start to see it's already discovered these. It's continuing to discover them. And it will grow. We will end up growing 4 or 5 layers. I'm limiting right now to 5 layers, but we can leave it unlimited. I've had system run up to maybe as many as 15 or 20 layers, and then it will collapse them down and eliminate the things it doesn't need. And it'll bring them back down to what's really 2 or 3 layers, but it might be primitive layer 0, layer 1, and then maybe layer 14 and 15. And then the other layers will go away over time because they're no longer necessary. They're included in the whole system. So we go here and look at this, and I can speed this up a little bit just to show you some things happen a little faster. I'm just going to let this run. It's not going to iterate for a minute. Let it run for about 30 seconds, and then I'll come back and we'll be way further down the line. So we're now up at 3,000, and you'll see about 7 microjoules. Memory is still at about 0.3 of a kilobyte, and you can kind of look through here. Goal-aligned learning is how many successful iterations have happened. And you'll see right here, I can't just highlight that one. We're using 56% of the calculations will be done at layer 5. And layer 5 is 2.6 times better than layer 4 in terms of efficiency, which is 2.6 times 3. 2.6 times 2 times 3 points. So that is a significant amount of savings. A significant amount of savings. I can't do that math in my head anymore. And then the last one I'll do just to show you is we'll go up and do the recursive maze. And it's the same thing. There is one path from here to here that's optimal. I can show you that path. That is the optimal path to get from point A to point B. It has to figure that out. Again, it's starting from scratch, doesn't know anything. I'm not preserving between these things. I'm going to go with something a little simpler here. There you see ICFA is running. And you'll notice that it's not always finding optimal. Sometimes it's going into corners and bouncing off the corner. It will get smarter and better. That was 120 steps. It's 109 steps is optimal. It will start learning a little more and be much more about finding the diagonal lines because they're less energy. It's going to run. Now, if we go back over here and look at how the brain is forming, we're still on layer 1, but we will have layer 2 and 3 and 4 show. And again, you'll see these will start to come down as we learn, and as we save more and more energy, they'll come down and become better and better. There's a whole lot of things I can show you guys at this point in time, but I want to answer questions and have some dialogue. So if you don't have anything else you want to see right now, I'll kind of leave this running and just let it run, and then we can start to talk a little bit and answer some questions. I know this was a drink from a fire hose, and I know there's a whole lot of stuff and you're seeing it for the first time. The point of showing you this is I think this can be something that would be a tool that you might be interested in using, and we will be able to provide this to you sometime next week to 2 weeks.
Thank you very much, Thomas. As is a tradition here, we will now turn off the mics and give you an applause. Um, yeah,
Thank you.
very, very interesting. Um, Super. So yeah, now let's go into the Q&A session. And just before we begin, Thomas Loker, is there anything, how can we best help you? Is it to answer the questions that you put in at the end of the presentation, or is there anything specific that you would like some comments on?
The first thing I'd like is just feedback in terms of, is this relevant? Does it make sense? What are the areas of questions that you have? I may not know the answers to them today. There'll be things that I want to work on and get back to. Um, we we built this so that we have a platform to actually compare active inference in the version that we're using it, for this concept of the fractal core, which is what we're putting in these devices that we're going to release to do a number of things. Initially, just to help identify the individual as the individual I expect them to be, to change the nature of how security works in the digital world. So that's the core of what we're doing now. But I need feedback because I don't have anybody that I talk to on a regular basis that knows much at all about active inference. The people that I know and talk to are programmers and developers. Even the guys that are doing AI have no understanding whatsoever about what individually centric systems are. Go into Claude and ask Claude to help you develop an individually centric system. It'll give you a design, and then when it goes to debug it, after the first debugging, it won't be an individually centric system ever again. It seems simple, but it's hard to conceptualize.
Right, right. Okay. So if anybody has some comments, please raise the hand and then feel free to give some feedback. Yes, Ein Culver.
I'm curious about the API that you're exposing to this model.
Um, there is no API exposed in the model, meaning in terms of sending data in and out of the model.
So, for example, in this maze scenario,
Uh-huh.
um, there are presumably commands that the agent can give to its motor primitives or its whatever actions are available to it.
Mm-hmm.
So, what is the API that inserts those actions?
I don't know that I have the skill, the technical capability to answer it. So let me try to explain what's happening. So right now, the only thing that's going on in terms of the system itself is we have the primitives, the 8 primitives down here. It can go north, south, east, west, yada yada yada. When it begins at the very start, when it starts at the very beginning of this process, it learns these and then it starts to try them in the maze. Let me go back here and let's go back to the simple maze. And we'll come down here. And you'll see as one comes up, it has tried various things and it's found what's necessary to go forward. The API, what's happening at this point in time in the system is the sensation of where the smell is of the cheese is being rated in an active inference's formula, based on the likelihood that that step is going to get it closer to the cheese or not. If it does get it closer to the cheese and it doesn't run into a wall and get stopped, it continues with that because it'll do it again and again. On the third pass through, it's now become, if you will, a unique entity in here. This has become what we call a CFC, which is a composite fractal core. It has a fractal core running in it. And this is now the dominant form of moving. And as long as it's successful, it just repeats it. It really is now, in effect, attenuating. It's just repeating this over and over and over again until it sees an error. Now, when it gets to the end of the path, it will see an error because it's got to go back to the beginning. So after 40 steps, it's coming back up here. But the only decision point that's being made is less a command and more choosing which motion that it can make is happening at any given point in time. Does that answer your question?
So to expand this a little bit, say you were to suddenly change the dimensionality of the maze, so suddenly there's more primitives available,
Mm-hmm.
then this
Well,
this system would still run.
oh yeah. So let's change the dimension of the maze. Let's do that. Let me take. I can't change the dimension in terms of the number. I have another maze that has more dimensions, but let me just do something I think that will give you an idea. So right now everything's in the southeast. So what it's really learned so far is the best move is southeast or southeast, 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 or four southeast in a row. It likes this one the best because it's using the least amount of energy in this case when it measures the energy use. So when I go back up here, let's change the entire maze. Let's reverse the maze. Let me put the end up here. That's where the cheese is. And let me move the start point down here. That's a very different thing. It's going to have to learn this now. So I'm going to go away from this. You know what it's going to do. It's going to find its way up here. I want to go down here and show you what happens when I resume. So now it's running. You see, it's already finding the other things. It's calculating a different move and finding that's getting me closer to my goal. So that is how it's learning additional moves. And now it's built layer 2 because now that it's got these other options, it can start to combine them. Now there's not much combination in this. I could do the same thing in the obstacle course. So let me reset this for a second. We're going to start from scratch and go over here. Going to do the same kind of thing here. I've got this going in the obstacle course. We'll go look. This is going to have a few more layers come up pretty quick. It's still predominantly southeast and south because it's got a few little obstacles. So we'll let that run for just a second so you can watch it progress. And we've got now 5 FractalCores running. Now let me go back up here. And I'm going to pause. I'm going to draw in a barrier to make this a little bit harder. And then we'll hit resume and we'll go watch this and you'll see a number of other things start to pop up quickly, which is it's now learning the change in that environment. So if you were using this like the game Pong where it's constantly moving, it would be learning all the time. It would be doing this all the time. And it would be pruning the things it isn't using very much anymore. If typically you're not ever in the corners over here, it would prune anything related to finding those corners and they would go away. Now this right now is fairly simple, but let's try one other thing. I want to pause this for just a second. And I'm going to go down here and I'm going to hide the cheese in a trick area. I'm going to take the cheese from here. I'm going to put it here. Now this is the optimal path. They don't see this. This is just my calculation of the optimal path. Now when I run it, it's going to find its way down here and in this little corner. How can it get in the corner? Because they don't have any dimension. So you see it's already finding that there's an obstacle and it's finding its way around. Boom, and it's found its way in. ICFA has found it. These guys will take quite a while to get there. In fact, in the maze situation, MCTS takes somewhere around 750,000 steps to solve the maze. We solve the maze in 120, 130 steps almost every single time, and we get down to optimal. If you watch here, our effective rate, our efficiency rate is 0.98 right now, and we will eventually get up to basically 100%.
So if I'm understanding this correctly, the cheese smell is the reward function.
Yeah, although there's no there's no reward in the classic machine learning sense. In other words, it's just it's achieving its objectives. So yeah, but it's not. The weighting is just variation. The only weighting that's going on here is whether or not that's more likely or not likely. It's not a classic reward function the way you would see it in most of the machine in all of these systems. All of these systems use some form of a reinforcement learning structure.
So when you first activate this agent, you can insert a setting saying maximize the likelihood of this signal.
The algorithm, the active inference algorithm already has that. This is just a standard active inference algorithm that is just following active inference protocol. It doesn't have an A matrix and it doesn't have a D matrix at this point in time in the system. It could, and that's one of the things right now we're trying to make sure we don't have it, because ultimately when we use this for one true U, if Apple adds another sensor, a different kind of sensor to their phone, they have 14 sensors now. Samsung has one phone with 17 sensors. We want the system to be able to just see the data come out of a sensor. We don't need to know what the data itself means. We just need to be able to determine the pattern that the data is delivering based on the correlation to the other data we have that's now correlated to the behaviors that you are doing. This sounds really weird, but ultimately we don't actually care about the meaning of the behaviors themselves. We can extrapolate them through other data later on in the phone. We can kind of figure out what you're trying to do, where you're trying to go. But the why it's happening, we don't care about. We just want to identify a pattern, note that that pattern is correlated to other patterns. And when the patterns are correlated, and the more they're correlated, the more we have confidence that you are you, that you're the only one you can be. We've got a system we've been working on with this thing now for the last year and a half, 2 years. We can get the 99.999999% accurate in our calculation that you are you with 5 sensors in a phone. And it's all being enabled by active inference. Now, this fractal core is the way we're actually going to deploy it. The ones that we're doing today are more basic statistical. They take more CPU, they take more data, they take training, they take all these other things. This is the thing we're building that will sit at the edge of the network and doesn't need really any of that. I would argue that this is close to the way the brain is going to be learning from day one. I don't know enough to know whether that's true or not, because I'm not a neurobiologist, but I'm exceedingly interested because I'm seeing this play out now all the time in all the systems we're doing. So I don't know if I actually answered your API thing. One of the points to make that's important for us at OneTrueU and IC Corporation, we never take any data off the phone, off the edge device. It's never transmitted anywhere. The only thing that's ever transmitted off that device to validate that you are you, Ian or Steve or Carl or Stanley or Jonathan or whoever, the only thing that goes off is what we call a confidence index. And the confidence index says we are 99.9997% confident that guy that I'm talking to that I think is Carl Friston is Carl Friston. Or the CPU that I think I'm connecting is the CPU, or the smartphone, or the thermostat, the smart thermostat. In other words, anything we now can validate because it's going to be cross-correlated to all the other things it can communicate with. We don't just look at the sensors like, accelerometer and gyroscope and GPS. We look at interconnects as well. Well, I'm sitting at this GPS location, my home in California, and I should be connected to a router that looks like this and acts like this and has these characteristics, and 2 smart televisions and my wife's cell phone. So this system, this OneTrueU system, is using active inference for every single one of these things, connections, senses, and it's finding the patterns in those things. And then I predict that this is going to be the next look for this pattern, and that pattern is achieved, then instead of just attenuating it at that point in time, I'm using that to validate that this is who I expect it to be. So if a hacker tries to hack into my computer and start doing things in my computer, it's not going to have the characteristics of what I expect it to have.
So my question then for that is, say you have a person who has a pretty routine way of interacting with their computer, and then offline they interact with somebody, and then they decide, okay, I'm going to change my process. Then is there not a risk here of the person being locked out of their own computer? Because
No, because it's not one measure. It's literally hundreds of measures and correlates. So and that's one. And two is think about the idea of grabbing a coffee cup. So and we actually have a mechanism to go after child predation, by the way. People that are going on Roblox and TikTok and gaming platforms to go after they're child predators. That person, when he's doing things in his life, when I go to pick up a coffee cup, I have I pick it up basically the same way. Why do I pick it up this way? Because active inference has learned this is the most efficient way for me to do it. That's the way I'm going to do it. I can fake all kinds of things, but I can't fake those little micro movements, those little micro moments. One, two. There's a theory. We haven't done anything with it at this point in time, but we've talked to 2 or 3 people, and there are theories that, as an example, a child predator, when they're behaving in a certain way, trying to pretend they're a 12-year-old or 13-year-old kid, they try to change the way they're behaving, but they can't change the micro movements. They can change the macro movements. So they believe they can detect the difference. When I'm trying to when I'm in the predation mode, I will have a characteristic behavior there. Can I have a characteristic behavior? Yes. But if I'm correlated to my computer, if I'm correlated to my GPS location, if I'm correlated to my typing, if I'm correlated to my voice, if I'm correlated to the way I'm moving and the things around me, then I'm still validated that I'm the person I'm supposed to be. I can change my hair. I had cancer taken out of my finger a few days ago. Still have my finger, fortunately, but I can't move. I can't use this hand to do anything. So for the last couple of days, I have not been able to use this hand to type, to do things that I normally do. My system still knows it's me because it's adapted. It's very rapidly been able to learn. Tom's not using his left hand, but that still has to be Tom. He sounds like Tom. He's connecting and talking to people that are the people he talks to on his phone. He's connected to his same router. That's still Tom. I can attenuate this information for the time being. It's not that big a deal. But if I was sitting in Danville, California, and then 5 minutes later, my signal's coming from Los Gatos, California, that would be an indication that there's a problem. And the reason is because I couldn't physically have made that transit that fast. So these are the kind of things that we can enable with this system. Did I answer your question?
somewhat, I suppose the concern that many people will have is over mass surveillance and how this could possibly backfire.
Well, that's another great question. That's a good observation, and that's part and core and process to the protections that we build in the system. The system exists on your device, your phone. We don't own it. We don't have servers. It's an edge of the network system running on your device. In fact, the software is going to be your software. We won't license it to you to use. You will own it. It's yours. The second thing is you can, if you choose to, encrypt and lock down everything on your phone. It will be encrypted and locked down to your personal, we'll call it ID, but it's not an ID. It's built into the FractalCore and the One True You system. So now when you're using your device, the device is yours, and you can set permissions on what application can run for people that aren't you, and only those applications that are you. So if I give you my phone, then it'll go off. But your point is about someone stealing your data. You can't steal your data from us because there's no honeypot. We don't take it and can put it anywhere. Two, it's people that begin to use one true you for personal security, like your bank and other things. They won't need your data either. They just need to know that you're the person you're supposed to be. They don't need to know all your personal information. They just need validation that you are the Ian you're supposed to be. So
So
it's
you're
your
trying
data
to
is your
create.
data. It stays on your phone. We don't ever take it off. The only thing that ever comes off the phone is the confidence index that validates the percentage that we believe you are you and only you.
So you're trying to create. You're trying to replace the ID with the cell phone, and
Well,
there's this
cell phone
predictive
or other
model.
things. Yeah, it could be a cell phone, it can be a tablet, it can be your desktop, it can be anything that you interact with.
And there's no risk here of people, in some sense, being compelled to stay within their expected
They can
behaviors
adapt, they can evolve.
quickly.
Yeah. Think about it the way you do every day, and I think I'd love to hear Carl's opinion, but active inference is our continual evolution to maintain homeostasis, to constantly be surviving and doing the things that bring us the best outcome in the long run. So as we adapt, as we change, each of these individual matrices will adapt and change. And if they adapt and change, we're using first, second, and third order derivatives to determine other things other than the data. Is the data changing? Yes. Is it changing within the first order derivative that we would expect it to change? Yes, then it's less suspect. Or is the velocity of change, the second order, a little different? We can look at these things to see if you're changing within a parameter that would give us comfort that that's where you should expect to be. None of these are binary decisions. They're all variational decisions based on the likelihood of the prediction of the model that you will be behaving this way. When you are behaving that way in a general sense with a variety of measures meeting up, those things are telling us that yes, you are still you and only you. These are great questions, by the way.
Okay. I'll think more about this.
Good. That's what I need. I need people to think on it.
Amazing. Thanks for the questions, Ian. Is there anyone else who has some questions? We still have some minutes before we move on to the next section with Carl's comments. Let's see. And Stephen, yes. Stephen, you can go ahead and unmute your microphone and post the question. Hmm, I don't see anything in the chat. His microphone is not working. If you want, you can write the question here in the chat, and then I will post it to Thomas. And then maybe in the meantime, I can. Oh, let's see. Yes, so Stephen, he asks, how can this be used in nefarious ways? Which I think we touched upon a little bit already with Ian's question.
Yeah, it's if the government, as an example, if it's individually centric, you're pretty well protected. And that's the reason this is individually, not enterprise. Enterprise-centric systems, because they are controlled and operated by the enterprise, and the enterprise has all the control and power. It's easy for me to go in and take control over a server that has all of the banking data Or you look at Google and Facebook, there was a hack at a data center last year that 158 million text-based, not encrypted, text-based IDs and passwords were stolen. 158 million. Very likely that some of our IDs and passwords have been stolen or sitting on the dark web right now because they're enterprise-centric. In the individual-centric system, the data that exists is your data. It sits on your system. You don't have to share it with anybody else unless contractually you have to. So use Facebook as an example. When you go into Facebook today, they scrape your system. They see what you're doing so they can feed you better advertising. You could say, I'm not willing to share any of that data with anybody and turn it off. They may come back and say, if you want to use our system for free, you need to share this data with us. Then you make a cognitive decision to do that. That's fine. But are there nefarious ways that individuals can go after other individuals? There probably are, but honestly, and this isn't a joke, for the last 20 years, we've been trying to think about every possible way that this can happen. Well, not really 20, maybe 10, that we've been focused on this side. And we believe we've covered all those bases by the rules and conditions under which this thing operates. If the data is locked on your phone, if it's encrypted to you in a dynamic encryption, these are not static encryptions. This is not a code or a key. This is a dynamic changing environment that is, when you're consistent with this environment, you're in it. If for some reason you got so aberrant in terms of your behavior that you couldn't, you would then contact us and there would be a way for us to reopen it. One of the questions that comes up is, well, what if I lose my phone? First off, if you lose your phone, nobody can open it. They can't use it because it's not you. The second thing is, if you get a new phone, you say, well, how long is it going to, how do I get back to where I was? You just plug the thing on. You just turn it on. And in a very short period of time, it's going to figure you out. Now, if you want us to do it, we can keep a backup of the components and metrics of the system, and we could reload it to your phone, but you can be back up and running in seconds. It takes about 20 to 25 milliseconds in this current thing for our voice recognition system to be able to determine it's my voice, 20 to 25 milliseconds with a high degree of accuracy. So there's lots of different things that in terms of ways we can pull these things forward and go forward. I would not say it's 100% foolproof. I just don't know right now from the traditional sense where we're exposed that graphically. And again, think about it. And if you come up with something, shoot me an email or get me a phone call and let's try and talk through it. We want to protect against all this. And again, by the way, One True You is going to be free to everybody, including banks and hospitals, enterprises. Enterprises will be able to deploy One True You for nothing. They don't have to license it. We will make our money later on when people start interchanging data. The long term of this is these are all smart neural network nodes with access to sensors and data, which people are going to want to have access to what's happening in those areas. So all of us will actually have sensor data, not personal data, but sensor data that we are more than willing to share with others. We are building what will become an interconnected set, a world network of neural network nodes that can be connected directly from device to device to device to Internet of Devices, et cetera, et cetera. With this system, with this kind of authentication verification system, we can now interconnect with everything.
So
That's the
what
goal.
is your business model in the sense of, you said you'd make money off of interchanging data?
Our business model is this, that for validation, as an example, every time you get validated by a bank or Facebook or whoever wants to prove that you're you, they will pay us somewhere between 2.5 cents at the high price down to well under 0.5 cent. And they will pay that for the validation fee. Twitter spends almost $800 million a year in technology to validate the users that are on Twitter. We could take that down to $9 million a year. So we could do it well. They don't do it well. So the idea is we will become really, at the end of the day, we're in the data interchange business. whether it's the confidence index initially or other data that people are willing to share. And the other point you should know is if people are sharing their data and other people are consuming their data for monetary purposes and paying for it, when they pay for it, 20% of the revenue that's generated by your data, you get back.
So you're giving users the option to sell access to their sensory telemetry.
Yes.
Okay.
Yep. And again, we have no servers. We don't have servers. We don't need servers. Everything that we're talking about exists on a device at the edge of the network,
Have
which
you ever
ultimately
considered
is if we build the system the right way, ultimately that's the way the world is going to work, just like people work. We all
have you
process at our local
considered
home, right?
have you considered tying this system with some form of UBI?
Consider it, yeah. Mhm.
Do you think that would be feasible given your current technical stack?
I don't know at this point. That's something that I'd have to discuss and look at it. Is it feasible? I don't know. I don't have enough knowledge in that area to be able to make that determination.
Mm. We'll have to move on soon, but maybe quickly before we do, Stephen, he has a follow-up here, where he
Uh-huh.
says, if it becomes an ID replacement, the key is confidence value validation. That becomes a leverage if it becomes a standard. I'm thinking of spoofing leverage, hostage taking. The key to understand its implications is to try to find how it can be used in ways you don't want it to be used.
Hmm.
So maybe a quick comment on that, and then we'll move on to the next.
So again, it's not a static measure, it's dynamic. And it's dynamic based on multiple variables that are all exchanging at any given point in time and correlates across all of those. It would be the concept of a quantum computer. Could a quantum computer do this? Not in its current form today. Not it's just too many dynamic calculations happening in real time. Um, so I don't see that that's a possible case in terms of how it would play. Um, Nothing is bulletproof. I mean, I'm 70 years old. I've been in business 50 years. I've learned a long time ago, never say never. Something always happens. And we won't solve every possible equation, but it looks like we can solve a huge amount of them. The other thing too is we keep talking about this thing, and what we say we're doing really is an architecture. It at this juncture, it kind of looks like software because that's how we're displaying it and putting it together. In the long run, this becomes an architectural change in how the world works, and we don't have to change the fundamentals of the internet or how people work or their workflow. So people can continue to do what they do, but they don't have to use IDs and passwords, number one. And in going in this direction, we now validate the provenance and pedigree, not just of the person, but of the device, of the data, and of everything else. So now I live in a world where if I send you something, not only do you receive what I sent you, but it's encoded in a way that you know it came from me and it's unadulterated in transit. So you can trust the data that you're getting, number one. And number two is later, if someone does take your data, you'll always be able to identify your data. And the system itself enforces it, not at any one point, but all interconnected points that are operating this way.
Hmm.
It's
Sure.
an enmeshed security system. And
Yeah.
again, does that answer all the questions? No, no, it does not, because there's too many questions that I don't even know to ask.
Yeah, that makes sense. Good. So now I think first of all, thank you for all the very good questions and feedback. Now we'll move on to some comments from Carl. So I give the mic to you, Carl.
Thank you.
It's
Hi
good to
there.
see your face.
It's nice to see you again. So it's my turn now. Excellent. That was a very, very impressive presentation and for an academic, a really interesting conversation about the deployment of this tech in the future. I'm going to sort of limit my feedback and comments to the sort of academic aspects and the active inference, and try to address your questions. And I'm aware that this is being recorded, so I'm going to sort of, tell you stuff that you already know, simply because I imagine that you might want to use this material to as a talking point to scaffold conversations with your developers or with your colleagues, or indeed your other project partners, in the future of time. And just to sort of take a perspective on that, I think that your presentation and the discussion afterwards, because it's been recorded, that's a really useful resource. And I'm just wondering whether you shouldn't pursue that agenda of building a set of YouTube or sort of interactive discussions, presentations as a resource for exposing the dialogue, in this instance with academia. But I'm just also wondering whether an Active Inference Institute live stream might be a useful resource for you. Again, exposing yourself to a different kind of community, a different set of agendas, a different set of questions, that I think will all be sort of useful in disseminating the foundations of this work, upon which you're now going to build in order to get to this sort of commercial product and the applications that you've been discussing. So I also want to answer your questions, those 4 questions, because there may be very simple answers, but to answer them in a way that is useful for this feedback. Who wrote the software? I mean, these graphics and this demonstration suite, this sort of Cognition Lab, it's extremely impressive. And so did you write this software?
I wrote it with significant help from Claude Code, and anti-gravity. I did not use my other developers who are building the product right now for our first deployment in a proof of concept test, because I don't have the time for them to focus on it. So since January this year, I just decided I was going to teach myself enough to be able to use those tools with the hope that they would work. At the beginning, they didn't work worth a damn. In the last 2 months, they've worked very well. So it's been me and the general concepts, and then using Claude and Claude Code to build it. And the biggest issue using Claude and Claude Code to build it is I can give them the definition of active inference. It'll build a good engine. And as soon as it goes to debug it, it's no longer active inference. So I had to constantly go and get it to build it. And when it went to debug it, I had to go back step by step by step and have it debug it. So it was still sticking with active inference.
Yeah. Okay. So I mean, you're in a world which I have no experience with or of, and I know you are an artist in using things like Claude and large language models to to get it to do what you want to do. At the back of my mind is the question: if I sort of suggest particular papers and particular not shortcuts, but sort of nuances of what you've done that may make things more efficient, will Claude be able to understand, given that the ideas are at the level of academic publications as opposed to exemplar code?
So I think Carl, I read papers all the time and have gotten to the point where I can understand, I'd say 90% of what it's doing. One of the things today about Claude, as an example, not so much ChatGPT and definitely not Microsoft, but you give an academic paper to Claude and Claude is damn good at going through it. I do this quite a bit when I'm trying to get when I was trying to get the system done. I would pull a paper, whether it was yours or a couple of them from Mark Sones and Lisa Barrett. I had one from her and I put it in and it extrapolated out of that formulas and understandings of how they were talking about the issue, and it used those things to help refine the ideas that I was using in this. So it's a phenomenally good tool if you manage it.
Yes, and as I say, you clearly are an expert in being able to manage it. Okay. Well, I'll proceed then under the understanding that Claude and you together can make some useful head or tails
Yes.
of the particular issues.
Right.
And in particular, I repeat, the four questions or four areas that you sort of wanted to discuss and unpack a bit more. Perhaps what I've done is, as usual in these sessions, I've gone through picking out a series of papers, largely to remind myself to celebrate a particular point you're making. Some of them are very abstract and they're just for the general public, as it were. Some of them are specific that might be sort of pragmatically useful for you. Could you share your screen again and just show me those
Oh
four
yeah, sure. Yeah. Yep. There you go.
Excellent. Can we go to the slide where you had the four questions that you'd like to discuss?
I sure can.
Brilliant. Okay. Right. So we've got implicit renormalizability, hidden state inference, partial prefix credit, and D matrix from experience. Okay. Um, So I'm just trying to memorize these so that I can make sure that they've all been dealt with. And perhaps it would be useful just to sort of preview the questions and discussion, and then possibly return to them when I come to going through the papers I had for you. Um,
Mm-hmm.
the implicit renormalizability, the way you were talking, it sounded as if you had in mind that the application of the renormalization group involves some renormalization that you have eluded or you don't need,
Right.
simply because you've got a self-similar or scale invariant hierarchy uh, of agents. You're calling. Um, Perhaps I can just ask you the fractal core. If you had to identify a mathematical construct within, for example, the Markov decision process models used for active inference, would that be
Mm-hmm.
the transition matrix? Would that be the B tensors that basically
Yes.
move you right? So I see.
Hey, Carl, one other point that I think to bring up. So typically, I've got the B tensor that's there. Um, when you get into looking at what we'll call a policy, um, what we're doing now is we're identifying two different forms almost of the same thing. One is what is the characteristic of an error condition? So learning what is the error itself. And then two is what is the policy, what is the fix, what is the solution for it. So if you think about it from the idea of not time, but you think about it from precedent outcome, we're looking at what we expect the outcome to be. If the outcome is not that, then what is the fix given what the prior two things were? So if there was a couple of steps before, what would be the most likely next answer? Instead of having to throw out a three-step bundle and throw it all out and repeat it, we keep the good steps, the steps that work, and then we only are focusing on the one that is where we see the potential error.
Right. And can I ask the sequence of steps, when you get a good sequence of steps, for example, that you might want to apply a partial prefix credit to, are they
Mhm.
explicitly encoded in the level or the scale above?
They are so I have a series of functions that happen here, like north, north, north. And when I have north, 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 and I've done that same thing three times, we now take that and move it up to the next layer.
Perfect.
And
Okay.
that becomes north, north, north. And it's used unless it sees that it's not north, 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 it's north, and then it doesn't work. And then it goes, instead of throwing the rest out when it knows the second one fails, it just shoots back down to the primitive, grabs the next likely candidate by its variational energy, and brings it back up. And now I try it. If it works, now I'm on to the next one. So I save time, save energy. And I can
Excellent.
have a
Yeah.
failure in a sequence and not have to throw the whole sequence out.
So I think you've just answered your partial prefix credit problem. That mechanics should in principle work beautifully in terms of picking out what subset of moves are likely to be rehearsed and likely to end up yielding your prior preferences. And in the mechanics of finding or discovering what sequences of moves do the job, where the job is defined operationally in terms of, for me, the expected free energy that scores the likelihood of a good or a preferred outcome. You are doing the renormalization group operators. So in terms of the implicit renormalizability, the very architecture you've just described is an implicit renormalization group.
Okay, good.
You've already done that. There's nothing else. There are no sort of rescaling or renormalizations,
Right.
in the sort of vernacular sense. You are renormalizing because you're just basically applying a kind of temporal dilatation. So what was a single move at one level now becomes or can be regarded as encoding a series of moves at the lower level, and a single move at the lower level in turn encodes or in terms of sort of top-down causation becomes a prescription for a series of moves. So you get series of moves, and just by that architecture, you are implementing effectively an RG operator, and you're just doing it with temporal scaling. There's nothing else you need to do. That is the heart of what has been done. So I think, as you say exactly, there is an implicit renormalization operator in play, and in this instance, it is most, I think, intuitively foregrounded by the grouping operator over time, that you're gathering together things that are sequences that are grouped over time in an ordinal fashion into one thing, and that is the grouping operator.
And let me add something to this. We're calling this Hebbian crystallization because, in effect, if each of those sets are nodes, right? Think of it like a neural network node. Well, then neurons that fire together wire together.
Indeed, and so do when there's a preferred outcome. Excellent. So let me just read from yes, yeah, it is. Yeah, absolutely. The interblanket or the communication between scales is exactly forming. It is doing that renormalization. So it's just the functions that you use to harvest stuff at the lower level. And in the reciprocal direction, the constraints offered by the higher level, that interlayer communication just is the renormalization, or a result of having a renormalizing model under the hood. And that is the formal operation with the so the RG operators you can split into a reduction and a grouping. And the grouping we just said is grouping over time. You could also do a reduction over space should you want to, but I don't think it's necessary in this particular instance, or certainly in the applications you're talking about. So you can say that I've actually reduced the dimensionality of my policies, for example, simply because I've now chunked them in a optimal way, in accord with the path of least action or maximum mutual information, or however you want to describe it. You're talking about sort of Hebbian efficiency in the context of learning. Now, the hidden state inference, that's interesting because you said explicitly you're not using D, and effectively you also said you're not using A matrices. And just to unpack
not in the classic sense. It's because the A matrix doesn't, and maybe this is semantic. It is the fact that we don't really use the A matrix because, in effect, what we're doing is getting that signal directly from the sensor.
Yeah. So again, I think that's an astute point, and you can certainly say we are not using an expressive A tensor or likelihood matrix because it's an identity mapping. It's a sort of, it's a directomorphism in the sense that there's no partially observed aspect in terms of noisy data.
Right. Right.
So from a maths point of view, you certainly are using an A tensor. It's just an identity mapping, and that basically means that there could one argue that then there aren't any hidden states because you're directly observing all the states because there's no noise, and I think you could certainly argue that. So you're saying the cognitive lab is fully observable. And I appreciate your thinking ahead to the application in terms of sort of the one true you. But in this, just from sticking to the sort of active inference MDP under MDP, the fully observable can come in two flavors. It could be that I get noiseless observations, which is what you've assumed here, and which probably is safe to assume in further applications. But there's another sense, though, in which you are actually already doing hidden state inference, in the sense that if you've now got sequences of moves that are causing your observations as you actively move through the maze, then those sequences are actually, if you like, latent states that are causing the observations. So I think you are actually doing hidden state inference. It's just that you're not at this stage dealing with noisy observations or ambiguous observations, which would require a more delicate likelihood mapping or a tensor, which would not be a simple isomorphism or identity matrix.
I want to. I'm sorry to interrupt again, but I want to come back to this point because I think it's important. I would argue one of the advantages to individually centric systems is the difference between hidden state and observable state is none.
I think it depends.
We can think about that and talk about that, but that's in the back of my mind, keeps coming back into this thing, is that from an enterprise point of view, from when I build enterprise software, when I have that thing that's not part of my Markov blanket that I'm working at, I really, the delta between observable and influenced state inside of that, if I'm at the edge of that blanket, I think is the same.
Yeah, I suspect that we're using the notion of a hidden or a latent state in a different way.
It could be.
So, a latent or a hidden state is the inferred cause beyond your Markov blanket. So all of this language is entirely compatible with a sort of a centric and sort of a local perspective. It's just how you understand the computations described as belief updating or active inference within a node, within say a fractal core, and whether you want to, and usually what the way that one interprets that is that they stand in the computations, the states of your say fractal core at any level in an implicit generative model. Stand in for the causes of observations on the Markov blanket or on the at the level below, which could indeed be the actual sensor space. So the notion of a hidden state is more it is something that stands in for stuff that can't be seen beyond your Markov blanket, and because you are basically implementing, indeed with the maze examples, you are actually implementing, realizing latent states, where the latent states live quite high in your deep model, or your high levels or scales in your model. So a trajectory or a path from one corner of the maze to another corner of the maze is not an observable state. It is a construct that is causing the time point by time point observations. So those observations are the observations. They're not random variables. They're real variables. but the thing that causes it is the policy that you're composing through these RG operators, renormalizing operators, by the very that is furnished for free by the very architecture that you're using. So my sense is that you are doing hidden state inference. It's just that you're using the notion of a hidden state, and in probably too nuanced way. It is just simply what it says on the tin. It says anything that causes something I can observe, and anything that's inside your computer, inside your fractal, your core, must therefore stand in for some cause of what you can actually see. So what I'm trying to say is that I don't think there are any questions about hidden state inference, but I will come back to that in answer to Ian's question later on, just using your example. The partial prefix credit, I think you've solved implicitly, and this speaks to an interesting issue about the coarse graining, the grouping operator implicit in doing the chunking, in doing sort of putting a pair of moves together, or a triplet of moves together, or 4 or 5 moves together. Most of the work that I've done has kept this problem really, really simple. So the coarse graining is always just in terms of pairs. So if I do a pair of moves and that's good, I now say, now at the next level, that pair is now a thing. And then if I have a pair of pairs and that's good, then I assign credit to that effectively, and I take that to the third level, and then pairs of pairs of pairs. So I've now got each, as we move up the level, I've got 2 to the power of n. It sounds as though you've been a little bit more sophisticated, and you've allowed for a variable number n at each level to the power of m to the power of n. So if you sort of dumb down a little bit and just restricted your compositions or your grouping operators or your coarse graining operators in time just to do pairs, you'd automatically solve this problem. But you would be restricted to things that sort of double in length every time you move up the scale. But you just accept or reject depending upon, again, the sort of the objective function at hand, which for the architecture would be an expected free energy, or a mutual information, or a cross entropy. So in principle, if you get the right architecture and the right sort of chunking or coarse graining in time, you should sort that out. It shouldn't be a problem for the partial prefix credit. It's I think a distraction from your point of view. And which could easily be resolved just by being more fine-grained in the way that you accumulate as you get deeper and deeper and deeper.
And we're kind of in the last 2 or 3 days, as we've been turning on these additional layers and building out this layering structure. One of the things that popped up was when we came to pruning behaviors that were not really necessary to keep. We started having an issue that it would prune something, and then the interconnect, the trace between the upper layer and the primitive would break.
Yes.
So we had to figure out how to identify at the that lowest level connection, which what we did is we actually froze layer 1, which is the first layer of abstraction. And as long as we've kept layer 1 active and intact, we always have been able to now reconnect down to the primitive. But we would get in that maze, we would get to where ICFA would get locked, and it would start oscillating because it couldn't figure out the next move, because it couldn't find the next move because the primitive had been cut out of the hierarchy. So we had to preserve that lowest connection to the primitive, which was an interesting thing to realize, and it's now working. I'm not 100% sure that that's the only issue, but we did solve it by keeping layer 1.
It might be, and I recognise that issue, and I'm going to return to that in relation to your sort of golden ratio later on. But one device that one can appeal to is to use the notion of curriculum learning, so that you sort of do quite a lot of acquisition to build layer 1, freeze that, then build layer 2, freeze that, then build layer 3 and freeze that. So extend the notion of freezing the first layer to all the layers. You lose a little bit of flexibility, so you have to relearn a model if the situation or the context changes, but you can avoid the problem you just spoke about by using this notion of curriculum learning.
Well,
it is a delicate
that's a good point. The way we solved that was being able to identify in a sequence the likelihood of a failure, like if in a 3T sequence, north, 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 in the second north, if it looked like we had a likelihood of a failure, we could then do what we're calling an executive decision from mama, who would then do a constraint that says, I want the primitive instead. So it would do the first one, which had a high degree of success. The second one, which now looked like it was not going to be as high a degree of success in the loop, it would cut that out, go all the way down to the primitive, choose the most likely primitive, pull it up, and then preserve the third step that way. So as long as we have access to the primitive, we can have a failure in a sequence or more than one failure in a sequence and bypass it to get to it. If we've made that choice and we've already begun it and we find there's an error because something comes up in line, boom, we go down to the primitive, grab that primitive, pull up. We only have eight decisions. We only have eight choices. And I didn't show you how fast this thing runs if I don't slow it down. You can't see it. So there's two ways to solve it. I don't know which is the better way to solve it. We'll have to look at it.
I guess it depends upon how context sensitive you want, well, the degree of context sensitivity you want to build into it, because there is an argument you need to keep the lower layers very, very expressive. So in this context, the third move might not be right, but there may be another context in which it was actually quite necessary. And so you don't want to throw it away.
Right.
You may want to contextualize it. And it sounds as though the MAMA level is providing a particular contextual constraint there.
That's what it is. It is reviewing the contextual constraint and finding what it thinks is the least cost path to get to the solution without throwing out the baby with the bathwater, to continue that analogy.
Well, I think that's a nice way to express it. And in my experience with these sort of these architectures, you've basically got to train the first layer on quite a lot of give it quite a lot of experience so that it sees everything, basically, because if you've seen it once and you can implement something which I think is mentioned in the papers, and certainly will be in the paper that I'll just briefly flash up for the recording record. If you have a training sequence where you use effectively a kind of Maxwell's demon, that you know that this training sequence always has good endings, then you know not to throw anything away. So this is slightly different from sort of the ideology behind machine learning. And sort of it sort of turns things on its head. So in machine learning and reinforcement learning in general, the philosophy would give it everything and tell it when something good happens. The alternative way of, if you like, labeling the endpoints of good trajectories or good sequences is just to say, I'm only going to give you sequences to learn that end in good points. And therefore you learn everything, keep everything, because you're carefully crafting or supervising the training data. So instead of using the value function or a cost function to sort of indicate which parts of these, or which transitions, for example, should be remembered in the B tensors or the fractal cores, you're using them to triage the data before any learning and then just let it learn rich and good stuff, very sparse stuff. So it's also extremely efficient in terms of the energy consumption and the size of the data you're training, because the training is, you use enriched training data that always has trajectories in it that end up where you want it. And if you do that, then you know you shouldn't be throwing away anything, certainly at the first level. And then you can do your renormalization to make it contextually robust. The D matrix from experience, yeah, absolutely. Yeah, the D matrix is just used to simulate psychophysics experiments and economic games experiments. In a real world application, you're going to have to infer the initial states in terms of what's going on. So you don't, the D matrix is not part of the ABC of Markov decision processes or active inference, other than just to get the thing rolling. It can be, and as you say, it is learned. In fact, the original, which I haven't brought up, but the original demonstration of this using the T maze, I think in a paper entitled "Active Inference and Learning," actually used the matrix to demonstrate that things can learn the context in which they're operating. So I think that would exactly be D matrix from experience. That would be an important functionality. But of course, if you're doing continual learning, you don't really need the D matrix because there's only one beginning to an incredible.
There's only one start. Yeah, the biggest issue for us with the D matrix is if we can eliminate it, then we don't have, when it comes to new sensors, the new sensor can become available to us we can create a module just to address it through the API inside a phone, as an example. And once we're getting the data signal, once we have the signal, we can use the signal itself to start to characterize the pattern of the signal. And again, it's the hardest thing because I'm dealing with the individual. I don't have to contextualize all the various parameters for all the various people and what it means to all the people on the planet. In other words, I don't need to know which two of 2, 2, 2, and 2 is the 2 I need to know. I don't care what the 2 is. I care, is there a pattern there? And is the pattern reproducible? And is the pattern indicative of an outcome that I can determine you're trying to achieve?
Yes, and that pattern will, I think, almost invariably unfold over time.
Yes, but the time frame, the thing that we learned about this is the time frame of the unfolding is exceedingly rapid in terms of the initialization of those patterns. And you brought up the thing earlier. You may not even trigger some patterns of exposure of the data on the front end. It's like using the reason that I use that open grid, the least cost path from beginning to end, as an example is because, and then I only expose really one move, southeast, 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 southeast. And I expose 3 potential candidates for concatenations of that. I don't expose anything else because it's not necessary. Nothing else is necessary. If I get southeast very quickly, southeast is my move to get from point A to point B. But when the cheese moves, now I have to be able to go back and, as you would say earlier, reconstruct, or in this case, learn what's something I didn't have to learn before. There is, in fact, another move I can take that I never had to take before. So from a homeostatic point of view, I've learned to control my arms and limbs, but I've never tried to control my arm in a reverse function. And now I'm doing that because some reason I have to do it. It's like with this damn finger problem. I can't pull up my pants with 2 hands. I've had to learn to pull my pants up with 1 hand. Exceedingly frustrating. But it's a perfect example. And it goes back to my nephew on the stairs, watching him to learn how to crawl up those stairs over the 4 hours of watching him test, come back, test, come back, test, come back, fall. I mean, it was fascinating to watch him learn to navigate. He had never navigated stairs until that day.
Oh, yeah. And I think that also speaks to this sort of context, being robust to changing context. Your finger operation being a good example of this. You don't want to throw away all the primitives just because they don't work in this context. You need them because you may
Right.
leverage them at in another context, and
Yeah.
that sort of speaks to a balance between how context sensitive do you want your model to be. And of course, when you're younger, you want it to be very context sensitive. So you're having more plasticity, you're going to revisit, throw away less. But when you're old, not as old as you, but as old as me, and then you can sort of say, well, my life's going to be pretty predictable. I don't need all those primitives. Anyway, let me. I don't want to wear you out, or indeed wear
No,
myself out.
I'm fine. You go as long as you want.
Can I share the screen now, and
Sure,
then just
sure,
quickly
sure,
go
sure.
through? This is going to be a stream of consciousness, and again, it's largely you know most of this work, but it's largely just for the recording, just to
Perfect.
emphasize and reiterate a couple of points, which hopefully that will share. Ah, good. Yeah. So the first one is not for you. It was really for Ian, if he's still here. And also to answer, an unasked question: why on earth was the active inference agent able to do things almost in an order of magnitude more efficiently in terms of sample efficiency, for example, and also, as you nicely demonstrated, the thermodynamic and computational efficiency. And that was a question which vexed people a lot, a decade or so ago. And this was one of a very early paper written by somebody who was an expert in sort of reinforcement learning treatments of Markov decision processes, and thinking about why is it that active inference can be so sample efficient. To try and summarize what the big move is. In most applications of machine learning, you're trying to optimize a state action policy. So you're trying to learn a mapping between what I observe and what I should do. And that means that you can then articulate mathematically a value function of the state that prescribes the most valuable action. The problem with that is it's completely context insensitive and very inefficient when it comes to planning. So the alternative would be to invoke planning as inference, as a way of choosing what to do next. But as soon as you do that, planning as inference means that you're now not trying to optimize a value function of the states. You now have to optimize a value functional of probability distributions over states. And those would be your inferred plans. And of course, in the full active inference instance, then those plans are counterfactual moves into the future, exploring what would happen if I did that, even if it's just one step ahead. But of course, in the future, you'd have the future now becomes based upon your posterior predictive densities. It now becomes a belief about the future. So you have to articulate now the cost function in terms of a functional of beliefs about states, not states in and of themselves. And that function, of course, is the variation-free energy. Or the expected free energy when it comes to planning. And that's why you can't get the sample efficiency you would get with active inference or planning as inference if you used learning or machine learning. It just cannot be done. Although what you can do with machine learning is learn to plan. You can learn to infer, sometimes called amortization. And therefore, if your plans are always, when enacted optimally, are always the same, you can learn that. But that's very inefficient, but you can do that. And most machine learning would be regarded as basically learning to infer. And when it's learning to infer what should be done, that would be basically learning to plan. Whereas active inference just does the planning. And I think that is another way of Thomas, addressing your question about hidden state inference. I think you're already doing that simply because you're using active inference. When you're using all your Q learning, there's no inference going on. It's all learning. It looks as if it's learning to infer, and it looks as if it's learning to plan, but it's not actually inferring. is optimizing a value function of the outcomes. So it's a fundamental move from AI based upon reinforcement learning to active inference, which echoes much of what Thomas was saying right at the beginning of his thing. So in brief, I just wanted to celebrate and just reinforce this notion of the individually-centric approach. I think that's exactly the right way to go. And one of the reasons, there are many reasons for it, and you've discussed them at length in conversation about the security and the implications and utility of having everything sort of local. From a sort of philosophical perspective, then the efficiency you get when you compare biometric architectures with I think of enterprise structures, I think Thomas was referring to them as, immediately tells you have to decentralize, you have to federate, and you basically have to predicate all your planning as inference and subsequent learning on local energy functionals, which is a move behind predictive coding, for example, as a replacement for backpropagation of errors, which is the move behind promoting in process or processing in memory or in memory processing as a key holy grail for current computer science. So to actually not only decentralize the graphics card of the processing, but actually decentralize the memory, and you put the processing into the memory in a really local way. So I'm just trying to say, I think that everybody wants to move in this direction. They all realize that this is the way to do it. In different fields, as a computer scientist or a theoretician, this paper is just promoting this ambition or aspiration from the point of view of theoretical neurobiology, and is running through all the different instances of this kind of mortal computation, in the sense that the software is so local and decentralized and so intimately tied to the substrate in which it is doing its computation, you cannot separate it. So if the user or the iPhone dies, so does the software or the functionality. So now it becomes truly mortal, and it becomes truly biometric and truly efficient.
Yeah. You eliminate the von Neumann problem.
Exactly. Yeah. So sometimes I can't remember whether that paper goes into it, but yeah, absolutely. That would be one. That would be a sort of computer scientist's read on it, that I've got a memory wall or I've got a von Neumann bottleneck, and it's costing me a nuclear power station to pay to actually do this. And if I can get rid of that, then I'm going to have a much more efficient way of doing it. But
if we can get Microsoft and Google and all those people to understand they don't need 3 Mile Island, we'll solve this problem.
Yes, although you have to think about why they haven't gone down that direction already.
You and I can have that conversation some other time.
I was interested with your and this again just wanted to endorse your little comment that time is how did you put it? It's all in the ordering.
It's a
Time.
bookkeeping. It's a bookkeeping
It's the
function.
bookkeeping, yeah. And it did remind me very much of treatments of active inference in the, or more generally, the free energy principle in terms of quantum information theory, where exactly the same spirit and observation really hits you in the face. It's all about sort of the bookkeeping of reading and writing in this particular formalism, using sort of category theory, but predicated on Chris Field's interpretation of a Markov blanket as a holographic screen. But he talks a lot about having a background free, by which he means there's no space and time in the sort of standard metric sense. It's all about the bookkeeping, and the bookkeeping is a tremendous resource. So he actually says that explicitly in subsequent treatments along these lines, using tensor neural networks as an example of this kind of.
So does Carlo Rovelli. I
Yeah.
had a pretty good conversation with him 5 or 6 months ago through a mutual friend, and he absolutely endorses the concept as well. He doesn't care much about individual centric and enterprise centric, but he is an individually centric individual. He just doesn't know it.
It's good one. I have a lot of respect for Ravelli. I think his treatment of physics, for example, is the closest you'll get to the free energy principle. It's all about
Oh yeah,
inference and measurement, and
yes.
putting the observer as the thing of center stage in terms of in terms of the physics, meteorologically speaking. Good. So I'm just endorsing that and pointing to you to a literature where that you would find a lot of support for that. This is not for you, but for those people. So Thomas was flashing up sort of various technical reports and the like. He's also extremely good at sort of just summarizing ideas on various blogs and Medium and the like. So I'm just flashing this up so we have a record on the recording of where you can go and read a little bit more about this in an accessible way. So this is what is this one? Is this a medium? Oh, it's a Medium, Medium article.
Yeah.
Why active influence needs its own lexicon. And then there's one, I think, which predates it. No, possibly afterwards. So this focuses more on the fractal structure, which from the point of view of the renormalization group and what we were just talking about can be read not so much as a fractional dimension, but the implicit scale invariance that you get when you're rinse, washing, repeating the same kind of belief updating or maths at each and every level after applying these RG operators. So there's a self-similarity that is normally associated with these fractional dimensional structures that we find in nature. So I'm sure that's a good read should one want to, and a short read. I didn't realize it. We're not even so short, right? There we have that. So I'm putting this here again just to reinforce the sort of the biomimetic importance of this nesting and scale invariant nesting of free energy minimizing processes within processes within processes at different scales. This is I don't think Claude is going to find this useful, but it's conceptually, I think, speaks to exactly the same issues when you apply it now to theoretical biology and evolutionary thinking. You can think of natural selection as just an instance of this kind of scale invariant self-organization and free energy minimizing process, where there's a lot of pressure on what Thomas was talking about in terms of the interlevel exchanges. How does, say, the genotype encoding certain aspects or putting priors on the phenotype, how does that top-down cause the dynamics of a phenotype, and how does the behavior of a phenotype at a faster time scale, the sequences of moves that a particular phenotype do, how is that going to be installed through bottom up causation or message passing or interactions at the level above. So there's some interesting takes on the sort of ubiquitous scale invariant application of self-evidencing or maximizing your ELBO. Again, Chris Fields was involved in that work along with a series of other biologists. Oh, yeah, I just put this here. Again, I'm not sure this is going to be useful for Claude, but certainly in terms of linking this sort of bookkeeping picture on time, and it's really just an orderly or ordinal sequence of jumps or moves or transitions. In fact, if you just look at the maths upon which much of the probabilistic formulation of the free energy principle rests. This is exactly the case explicitly in terms of the definition of a pullback attractor. So that that there is no sort of continuous time. It's just basically what sequences of moves do you make, and how do you pull back those sequences to get out the underlying characteristic set or attracting set of things that your machine will do. And of course, the free energy principle is just about describing the behavior of systems that have Markov blanket partitions that possess, by definition, a pullback attractor. So right at its heart, the maths does speak to this bookkeeping notion of time, and if you like, getting to the weeds. Again, I don't think Claude's going to find this particularly useful, but certainly as a theoretician, it's I think a really important observation and link that joins the fields of random dynamical systems to belief updating in the way that's been described when you've got a Markov blanket in play.
I'll tell you that Claude knows that, by the way, because I have that paper and I did feed that paper into Claude when I was working on this.
Brilliant. This is, I imagine, where most of the Claude's most of the material you and Claude would have harvested in virtue of your reference to renormalizing generative models. I'll just reiterate, because it may be a useful thing for you to consider, that within this work also was this notion of this sort of Maxwell's demon applied to training data, to carefully curate the training data, not just in terms of labeling when good things happen, but actually curate the data so that the data, the transitions in the data points themselves become meaningful in the sense that they end up on the pullback attractor. That may be practically an interesting way to increase even more the efficiency, the sample efficiency of your learning, for example, in the Cognitive Lab demonstrations that you showed them. So just a little, I think, I can't remember if it was explicitly called Maxwell's demon. Perhaps it was around here somewhere. No, it's later on in the paper, but that's wasting our time. Just two more technical points now that may or may not be useful for you in conjunction with Claude. The first one is the notion of inductive inference that allows you to do extremely long paths once you've got a very precise model of what could be done and what can be done. Before you were talking about, well, there aren't any hidden states because everything is observable. And of course, once you get deep into a generative model, you're not talking about observables anymore. You're just talking about posterior expectations, but they can also be observable in the limit that they become infinitely precise posteriors. When they become infinitely precise or close to becoming precise, you can now threshold your B tensors, your transitions, your FractalCores, and just basically say that's good enough to be 100% and that's zero. That just cannot happen. So you just basically map from tensors that have this quantitative interpretation in terms of probabilistic transitions from one state to the next state, for example. You can move it to the space of logical tensors, where the tensors are actually encoded with logical, with true or false. So you can go from sort of floating point down to sort of, 1 bit, basically 1 bit encodings. If you can do that, then you can do your planning in terms of composing sequences of moves into the future from one part of the maze to another part of the maze to see whether the cheese odor has increased or not. And building in the constraints that you have learned, because this is something you deploy after you've got a precise model of the maze. So you know which moves you can't make. You can't go through walls, for example, but you can do diagonal across open corners, for example. So you install what you know about your maze, your particular operating domain, into these B tensors that have been accumulated probabilistically, probably with Dirichlet counts, but then you threshold them, you convert them into logical operators. And then you can use this device called inductive inference, described in this paper, Activities of Intentional Behavior, to very, very quickly, very efficiently roll out a long way into the future. And what you can do here is a kind of backwards induction. In the sense, because you can do this very quickly, you can sort of roll out into the future, and then roll back again from the future, from the good outcomes, from the things that Mama likes. And that basically provides you with constraints on what to do next. And then you can use conventional active inference to pick the next best move that maximizes the expected utility in terms of smelling the cheese. Or an increase in the probability of smelling the cheese. You can apply that, but within a very limited set of potential paths into the future that you've constrained by rolling out into the future a long way, and then rolling back from the desired states and a long way in the future back into the present. And it's a really, really efficient way of doing deep planning. Far more efficient than the Monte Carlo tree search approach. But it does rest, I repeat, on having either having very precise beliefs about the transitions that are ordered in time, in the bookkeeping sense, or converting them into very precise beliefs from a sort of relatively precise probabilistic encoding. But if you can do that, that can sometimes speed up the efficiency markedly, in terms of just because you're working with logical operators, basically, and you can do really sort of constrained tree searches very efficiently.
I have a mission, Carl. Before you get to your last point, I have a mission. My mission is going to get you to convert from temporal to outcome driven. Yeah, because temporal in and of itself creates a time problem. But if it's a precedent outcome, if we identify it as the outcome can be precedent for quite a while. It just I can't get to the subsequent outcome until the precedent outcome is full. It's an atemporal structure.
Yes, yes. The reason I didn't respond immediately was that I think that's implicit in this inductive inference. You're talking about a series of discrete steps. That so you've only got you're only sort of very much like a tree search. You're just sort of jumping to the next possible set of states and then jumping to the next possible set of states. Right. All inductive inference does is it is outcome based. It's just after this I will be potentially, I could be in this subset of outcomes. Right. And then you just label, well, these are good ones and these are bad ones, and then you reverse the process. And in reversing the process, you now know what not to do. I think that's probably intuitively, that's probably the best way of describing it. So the inductive inference is there. It tells you what not to do next, because if you go down that path, there is no potential route to your good space of outcomes.
Yes, and if you eliminate time from the from the process itself, you're now only you're only tracing to precedent outcome and finding that one precedent outcome that didn't achieve.
Right.
And so this is the thing that was the realization when I started coding this. Is prior to that, I kept getting dragged into using time because it was the only thing Claude could remember to do. And every time it would drop over there, things would start to slow down and things would break. And as soon as I'd get him back on the issue of focusing on precedent outcome, not time, precedent outcome, things became lightning fast because it's not It's not going through a cycle to get to something. It is either there or it's not there. If it's not there, address it.
All right, I'm just wondering
It's really hard to wrap your head around this.
yeah, and could be, I think, interesting related to this sort of composition of push forward and pullback operators. But
Oh,
let's not confuse ourselves with that
yeah.
at the moment. The final point I wanted to make was your golden ratio.
Mhm.
In in the way that we implement these renormalizing generative models, we score the model as basically encoded by the accumulated Dirichlet counts in the B tensors at, possibly a number of different levels in terms of the implicit mutual information. And
Mhm.
that is if you like, the average expected free energy, or a form of log probability or log marginal likelihood. And we only sort of include something, some transition, for example, making the sort of B tensors slightly bigger, or a new policy, a new move that you were illustrating in terms of, uh, including and then triaging or pruning at a later stage various sequences of elemental moves, or indeed the primitive moves themselves. The criteria that is used in this active selection aspect of active inference is whether there has been an increase or decrease in the marginal likelihood of the model evidence as scored by the mutual information
Mhm.
in these A tensors and these B tensors. But the point I wanted to make was that um, the, the rationale for including or getting rid of it is based upon something called a likelihood odds ratio, or a Bayes factor, also
Mhm.
known as Occam's window or Occam's
Right.
razor.
Right.
So if you fall without or out with Occam's window, then if it's in a good direction, you keep it and it becomes part of your model. You can grow your
Mhm.
model. If it doesn't, you lose it, and we get
Mhm.
back to the sort of triaging and the pruning and the removing redundant components we're talking about. On that view, one efficient way of doing the pruning is to evaluate the marginal likelihood if you removed something, and
Mhm.
then you take the difference in the log marginal likelihood. So if the marginal, or as scored by the variation free energy on the mutual information,
Mhm.
if that difference is greater than Occam's window, you reject it if it's going
Right.
down.
Mhm.
If it's not going down, then you keep it. And if it
Mhm.
sorry, if it goes up when you remove it, then you remove it. Um, but of course, all that rests on defining a threshold that defines
Mhm.
that window. I think that's your cube. I think what
Mhm.
that's basically, at the level of model selection, that's the
Right.
confidence that this model is better than that model, as scored by a log odds ratio, which can also be read as a log Bayes factor. Now, the
Mhm.
reason that sort of came to mind is that your choice of the golden ratio is very interesting. It is exactly the log odds ratio you would use with a classical alpha 0.05 statistical threshold. So if you
Mhm.
take the cumulative integral of a z-score or a Gaussian, at p is less than 0.05, you get 1.6.
Right.
So I think your golden ratio is perfectly licensed because you can interpret it, providing it is actually a log probability, providing your threshold is actually expressed in terms of log probabilities, as most sort of confidence intervals or statistics are. You've now got a way, because it's a natural log, they're called natural units. So 1.6
Yep.
whatever natural units is the natural is the natural way of
Right.
sort of accepting or rejecting, say, a null hypothesis. Um, And interestingly, it brings you very close to the Landauer limit for belief updating.
Yes.
So it's not so the Landauer limit would be predicated on a log to the base 2 of 1 unit, one bit basically.
Right.
So one
Right.
bit I think is something. It's not a no. I have to double check it, but hopefully you'll find that one bit, which defines the Landauer bound or the Landauer limit, is very close to your golden ratio in natural units. So I think
Well, so this is exceedingly interesting because I wrote that paper with Cheval on the causality of time, and one of the things we predict in there is that the failure of a blanket state of the blanket itself is not going to be gradual. It's going to get to a very specific point and it's going to fail. And when we were working on it, we kept coming back to this number, not having it in my head that it was a golden ratio ever. It wasn't part of my vernacular at that point in time. So the paper got published on ResearchGate, put out on ResearchGate, and 3 different researchers independently read the paper. And I got emails from all of them over the space of 2 weeks. One of them, the first one, is a guy named Arturo Salazar Chon in Mexico or down in South America. And he's working on analyzing epileptic seizures. And he's looking at the relationships between what he's considering the wavelength of the standing wave of the quantum state and the brain waves that are going on top of it. And he's been analyzing the waves where the waves kind of go like this. And then what's happening is the waves get discordant. And when they get discordant, they get to a point where everything fails all at once. And guess what that number is? The number is the reciprocal of the 6.18 golden ratio, and the number is off a little bit by the width of the corridor that's being calculated. So it's the center point of the corridor, and it's the inclusion of the noise in the center point of the corridor. And another guy named Lee Layton is doing the same thing. He suffers from almost a perpetual heart attack. He's been studying it there. He's been looking at something very similar. He came back to the same conclusion. And then a guy in Japan named Satoru Watanabe is working on Alzheimer's disease. And he's looking at the buildup of plaque, and he's calculating something very similar, not from the electronic wave point of view, a different point of view, and he's coming to the same number. And they're all coming to the number, and the number variance is the width of the corridor. So I don't know what to do with this. I mean, somebody else is going to have to chase this. The math is beyond me. But we started using this as a result of them finding this number. We had looked at it before, but in the paper, but we hadn't really done much with it until they came back and said, "We just want to let you know we validated your causality of time paper." I thanked them very much, and then started trying to understand what the hell it meant. And then we came back in, and that's when I said, well, let's start using that number here for these two, the upper and lower bound of the confidence corridor. So I didn't really show you this in the lab, but in the lab on ICFA, since we're doing active inference, not reinforcement learning, I have the confidence corridor and I have the spread of what's happening, and I can see critical, stable, and I forget what the third term I put in there, but the 3 layers of one is going to fail, one is not going to fail, and the stable part in the middle. And those numbers are constantly showing up in these calculations right in that general range. So we're seeing it over and over again. Now, part of the reason we're seeing it is because we're using it as the benchmark in the lever, and I think that's influencing it. But this golden ratio thing is something that we all have to start to think a little bit about and stop discounting so rapidly.
Yeah. Just listening to you talk about this confidence corridor, that it just strikes me that's and gives you an easy entree into an Occam's window. It's
it's exactly what it is. In fact, The confidence corridor is calculated primarily as the center point is the ratio between complexity and simplicity, or efficiency, precision.
Yes.
It's exactly the point. And I'm just using these bounds as the initial set bounds for where the edges of the boundary should be, and then we're measuring where the edges of the boundary are as the structure is moving up, as the system is tuning itself and learning itself, we're measuring where those things are falling.
Yes, that's interesting. It reminds me of some work where people actually just measure the fluctuations in the free energy just to sort of assess whether things are failing. For example, if you get a
Yeah.
component failing on a circuit board, or there's some phenotype in an ecosystem that's not adaptively fitting, then it
But
would be reflected.
what we're seeing is failure becomes a catastrophic point, and that it doesn't continually to gradually go down. That's what Sean found out in the epilepsy data, was that at the point of epilepsy, it doesn't just start to continually gradually build. It gets to a point, and from the prediction of the time issue is the blanket dissipates. In other words, it's a destruction of the blanket itself. So if you think of the drop of water or drop of ink in water, if it is encapsulating itself and keeping itself, it's keeping its boundary. But at some point in time, it's done. In other words, it's the destruction of the blanket itself.
Yes, yes, and which is entirely consistent with the free energy principle, saying that this is a
Yeah,
bound on the dissipation or the
yeah,
non-dissipation of the
yeah.
blanketed system itself.
And
Fascinating.
it seems to keep coming back to the reciprocal of the 0.618 number, or at least within the proximity of it. And right now, it looks like the proximity is based on the noise or the edges of the bound itself, the width of the corridor. And if you
Right.
look
Well,
at stock, if you do the same thing with stock and you use Bollinger Bands, you come up with the same thing. You see it in stock trading all the time with Bollinger Bands. They widen and they get close together. They widen and close. But when something falls off the bottom of the Bollinger Band from a stock point of view, that's when you see it go. The bottom literally drops out from under it until it hits its base stasis, and then it builds back up. So yeah, from the math point of view, it's beyond me, but it's interesting.
it is. Yeah. Yes. Beyond me. That's it. I have nothing more to say. Thank you very much indeed, and
Thank
congratulations.
you. Yeah.
Yes. So thank you very much, everyone, for the feedback, and thank you, Thomas, again for the presentation. We'll give you one last round of applause. So thank you very much.
Yes. Thank you. Thank you. Thank you.
Yes, and that was it for today. The talk will be uploaded to our YouTube channel by the end of the day or tomorrow sometime, and
Right.
then I'll send you, Thomas, a link to it as well so that you have it.
Perfect.
Other than that, thanks for now, and see you guys next time.
Thanks, Carl. Thanks, everybody. Nice to meet all of you.
Thank you.
See you.